Different hearts, different dreams. Injective souls ignite the beams. No dream alone, no path ignored. Surjective wills knock every door. More hearts to thrive, or more dreams to grow. Two mighty sets now march toward battle. The wings of cardinality raise us high to the heaven of infinity, beyond the sky.
Previously, we discussed the concept of a left inverse and a right inverse of a function. Without giving formal proofs, we stated the property that having a left inverse is equivalent to the function being injective, and having a right inverse is equivalent to the function being surjective. In this section, we will continue by discussing the inverse of a function. Let's begin with the definition. Let f be a function from a set A to a set B. We call a function from B back to A the inverse of f, if both of the following hold. First, composing f inverse with f gives the identity function on the domain A. Second, composing f with f inverse gives the identity function on the codomain B. In other words, f inverse acts both as a left inverse and as a right inverse of the function f. Recall that, equivalently, this means f is both injective and surjective, and hence bijective. To see an example, consider a function f from the set of non-negative real numbers to itself, defined by fx equals x squared. Note that f is indeed bijective. We can define the inverse of f, which is also a function from the non-negative real numbers to itself, by setting f inverse y equal to the square root of y. We can easily verify that the two conditions mentioned in the previous definition hold true. As a result, the function we have defined is indeed the inverse of f. The graph of f and the graph of f inverse are shown below. Now recall that when we previously studied left inverses and right inverses, our example showed that such inverses, even if they exist, are not necessarily unique. There can be multiple left inverses, but no right inverse, or multiple right inverses, but no left inverse. Now that we have introduced the inverse of a function, the first natural question to ask is the inverse unique? The answer is yes. If it exists, then it is unique. To prove this, we first state and prove a lemma. Let f be a function from a set A to a set B. Suppose f has both a left inverse, called g, and a right inverse, called h. Then g and h must be identical. That is, they are the same function. Note that g and h already have the same domain and codomain by definition. So to prove they are equal as functions, we just need to show that for every element y in B, gy equals hy. Now consider the composition. H composed with f composed with g, applied to y. On one hand, since h composed with f is the identity function on B, this is equal to the identity function on B composed with g, applied to y. That gives us gy. On the other hand, since f composed with g is the identity function on A, the same composition is equal to h composed with the identity function on A applied to y. That gives us hy. Comparing both expressions, we find that hy equals gy for any y in B. Hence, g and h are the same function. The lemma tells us that while an injective function may have many left inverses, if it has a right inverse, then all left inverses become identical and agree with that right inverse. Likewise, a surjective function may have many right inverses, but if it has a left inverse, then all right inverses become identical and agree with that left inverse. With this lemma in hand, it is now very easy to prove that the inverse of a function, if it exists, must be unique. Suppose both g and h are inverses of f. Then by definition, both g and h are left inverses and right inverses at the same time. In particular, since g is a left inverse and h is a right inverse, applying the previous lemma shows that g and h must be the same function, therefore the uniqueness of the inverse function. Let's look at some examples. First, let f be a function from the real numbers to the real numbers. We say that f is t-periodic for some positive number t if, for any real number x, fx plus t equals fx. As you can see, a t-periodic function cannot be injective, since different elements in the domain that differ by t are mapped to the same value in the codomain. As a result, f is not bijective and therefore not invertible. Next, consider a function from the real numbers to the real numbers that is strictly increasing. This means that for any two real numbers, x1 and x2, if x1 is greater than x2, then fx1 is greater than fx2. Clearly, the strict monotonicity implies the injectivity. If, in addition, the function is also surjective, then it is bijective, and therefore invertible. Finally, let's return to an example of an elementary function from the real numbers to the real numbers, namely the sine function fx equals sine x, which we are already familiar with from high school. This function is 2π periodic. As a result, it is not injective, as we have discussed earlier. Since it is not injective, it is not bijective, and therefore an inverse does not exist. Yet it is strictly increasing from negative π over 2 to π over 2, onto the interval from -1 to 1. Therefore, after such a restriction, it becomes bijective and has an inverse function, gy equals arcsine of y. You have now seen through examples the connection between bijectivity and the existence of an inverse. In the next section, we will present rigorous proofs of the key results that we have used so far.
신라 텐세